Hello everyone, we are pleased to present the current progress of our ANRF-funded research project titled Development of Efficient Cooling Techniques for High-Power EV Electronics. This research is being carried out at the Indian Institute of Technology Mandi under the guidance of our principal investigators, Dr. Sarthak Engg and Dr. Moumita Das, and our research team. Now let us begin by understanding why this work is important. Modern electric vehicles rely on compact power electronic converters to efficiently control and transfer electrical energy. Although these converters are highly efficient, they generate a considerable amount of heat while operating. If this heat is not removed effectively, the electronic components experience higher temperatures, which can reduce efficiency, shorten their lifespan, and even lead to system failure. A simple everyday example is a mobile phone or laptop. When it overheats, it becomes slower and less reliable. The same principle applies to electric vehicle power electronics, but at much higher power levels. Therefore, efficient thermal management is essential for ensuring safe operation, improving energy efficiency, and increasing the durability of electric vehicles. This challenge forms the motivation behind our research. To address this challenge, we have defined several key objectives for our project. First, we develop detailed thermal models of GaN-based power converters using ANSYS IcePack. Next, we investigate different heat sink geometries and airflow conditions to identify cooling configurations that provide better heat dissipation. At the same time, we are developing a dedicated experimental platform that allows us to validate our simulation results under controlled laboratory conditions. Finally, our goal is to establish an optimized cooling strategy that can improve reliability while reducing operating temperatures and energy losses in future electric vehicle power electronics. This slide summarizes the work completed so far. We first developed a detailed three-dimensional thermal model of the GaN-based converter using ANSYS IcePack. Using this model, we evaluated different heat sink configurations, including plate heat sinks, cylindrical pin-fin heat sinks, and conical pin-fin heat sinks. We also studied different airflow directions and compared top-mounted and bottom-mounted cooling arrangements. These simulations helped us understand how heat spreads through the converter and identify the most effective cooling configurations before manufacturing any physical prototypes. At the same time, we started developing our experimental setup, which will later be used to validate these simulation results. While numerical simulations provide valuable insights, experimental validation is equally important. For this purpose, we are developing a dedicated experimental platform. At the center of this setup is a specially designed copper block that reproduces the thermal conditions experienced by the actual power electronic converter. Embedded heating elements generate a controlled heat load, while multiple thermocouples continuously measure temperatures at different locations. The upper section of this slide shows the copper block assembly and its important components. The lower section presents our electronics experimental setup, which includes the GaN evaluation board, digital oscilloscope, programmable DC power supply, electronic load, current probe, voltage probe, and inductor. This setup enables us to evaluate both the electrical and thermal behavior of the converter under realistic operating conditions. Once completed, the experimental measurements will be directly compared with our simulation results to verify their accuracy. After developing the thermal model, we evaluated several cooling configurations. The temperature contours shown here illustrate how heat is distributed across the converter for different heat sink designs. Among the configurations studied, pin-fin heat sinks demonstrated superior cooling performance because they provide a larger surface area for heat transfer. We also observed that airflow direction has a significant influence on cooling efficiency. Additionally, placing the heat sink on the top side of the PCB generally resulted in better thermal performance because it is closer to the primary heat source and also benefits from natural convection. These findings help us identify promising designs before building physical prototypes, reducing both development time and cost. Let us now briefly understand the science behind our work in simple terms. Heat naturally flows from hotter objects to cooler surroundings. Our objective is to provide an efficient path for this heat to leave the electronic device. Heat first travels from the semiconductor into the copper base, then into the heat sink, and finally into the surrounding air. A larger heat sink surface allows more heat to escape, while proper airflow continuously removes the warm air and replaces it with cooler air. When these two processes work together effectively, the operating temperature decreases, the temperature distribution becomes more uniform, and the reliability of the electronic system improves significantly. Although the science is straightforward, optimizing these cooling mechanisms requires careful simulation and experimental validation. The next important question is why this research matters. Although our study focuses on cooling a power electronic converter, its impact extends far beyond a single electronic device. Today, electronic systems are becoming smaller, faster, and more powerful. Whether it is an electric vehicle, a renewable energy system, industrial automation, aerospace electronics, or even modern data centers, every system generates heat during operation. If this heat is not managed properly, efficiency decreases, components age more quickly, maintenance costs increase, and overall system reliability is reduced. Through our research, we aim to develop smarter and more efficient cooling techniques that maintain safe operating temperatures while improving energy efficiency. Better cooling also allows engineers to design more compact and lightweight electronic systems without compromising performance. For electric vehicles, this means more reliable power converters, improved energy efficiency, longer component life, and ultimately a better driving experience. In simple words, this research is not only about cooling electronic devices, it is about enabling safer, more reliable, and more sustainable technologies for the future. Looking ahead, several important milestones remain in this project. So far, we have successfully completed the thermal modeling, investigated multiple heatsink designs, analyzed airflow behavior, and developed our experimental platform. Our immediate next step is to complete the experimental validation. Using the copper block setup and the electronics test bench, we will perform controlled experiments and measure temperatures under different operating conditions. These experimental measurements will then be compared directly with the predictions obtained from our ANSYS IcePack simulations. This comparison is essential because it helps us verify the accuracy of our numerical models and identify areas for further improvement. Based on these validated models, we will optimize the heatsink geometry, airflow conditions, and cooling strategy to achieve the best possible thermal performance. In the long term, we aim to extend this work toward digital twin technology, where real-time experimental measurements and numerical simulations work together to continuously monitor and predict the thermal behavior of power electronic systems. Ultimately, our vision is to contribute towards the development of efficient, reliable, and sustainable thermal management solutions for future electric vehicles and other advanced electronic technologies. Finally, we would like to express our sincere gratitude to everyone who has contributed to the success of this project. We gratefully acknowledge the financial support provided by the Anusandhan National Research Foundation, which has made this research possible. We also thank the Indian Institute of Technology Mandi for providing excellent research facilities and infrastructure. We sincerely acknowledge our collaborating institutions, IIT Bombay, IIT Roorkee, and CSIR-CE IRI, for their valuable technical discussions, collaborative support, and research guidance. Our heartfelt thanks go to our principal investigators, Dr. Moumita Das and Dr. Sarthak Nag, for their continuous encouragement, technical guidance, and leadership throughout this project. Finally, we thank every member of our research team, Mr. Amit Verma, Tech Research students, Mr. Naseem Akhtar, Research Associate, Mr. Abhinandan Bhardwaj, a PhD student, for their dedication and contributions. Thank you very much for your time and attention. We look forward to your valuable questions and feedback.